In this session, we'll look at the three basic latches: the NAND latch, the NOR latch, and the D latch. Last time we looked at how a NAND latch works. Remember that all a latch is a simple storage device. We have two inputs, a set and a reset, and we can tell by the inversion bars here that these inputs are active low. With the two inputs, we know there are four possible combinations. When set is active and reset is inactive, we know that our output Q is going to set. When reset is active and set is inactive, we know that our device is going to reset. When they're both inactive, down here, we know that it's going to hold whatever value it has. And then we have the odd case out when they're both active at the same time, which is something that we really don't want to happen because our system is going to go into an unstable situation. So we don't want that to happen at all. So if we look at our waveforms here, we can see that we're starting off with both of them inactive, which gives us a Q output of low. We have a set happening here, so Q goes high, and it's going to stay high until we get a reset right here. It's going to stay low until we get a set right here. It's going to stay set or high until we get a reset right here, in which case it goes low again. If for some reason both inputs become active at the same time, the latch will become unstable and will stay that way until it gets a valid set pulse or a valid reset pulse. We should do everything that we can to prevent these inputs from going low at the same time. A NOR latch operates pretty much the same way. When it gets a set, Q is going to go high. When it gets a reset, Q is going to go low. But notice that the inputs here are now active high. There's no inversion bar there anymore. What that means is that we're going to be looking for a set here with set high and reset low. We'll mark that in. We'll be looking for a reset here when reset is high and set is low. We'll be looking for a hold when they're both inactive, which is when they're both low now. And the last case down here, when they're both active, again causes the system or device to be unstable, so we don't want to go there. Now, a couple of things you need to notice here. We already talked about the fact that the set input and reset inputs are active high now, but look at Q and Q naught. They're different from before. So our set input is responsible for controlling Q naught, and our reset input along with Q naught is responsible for controlling Q. So be careful if you're looking at the internals to make sure that Q naught is driven from S and Q is driven from R. If we look at our output down here, we can see that our set and reset pulses are now active high instead of low. So most of the time these waveforms are in the low state. So let's move forward in time. Q starts low. We get a set pulse right here, so set goes high, or Q goes high. It stays high until we get a reset right here, so Q goes low, and it's going to stay low until we get a set up here. Stays set or high, storing a 1 until we get a reset right here. Q drops down, it's now storing a 0. These two basic latches are quite simple to construct and use if we need a simple storage device, but the instability that can result if both the inputs are active at the same time is a real problem. So to prevent this from happening, designers added a little more circuitry out front and created a D latch, which is always stable. The D latch is also called a transparent latch. It has two inputs, D and DN. The D input is for the bit stream that holds the actual data that's going to be stored in the latch, and the enable is like an on-off switch. If enable is high, the latch is on. If it's low, the latch is off or disabled, and it's going to hold on to whatever data it currently has. So if we look at the truth table, we have enable off here, which means the data is going to be held. So whatever it is, it's going to hold it. If, on the other hand, enable is high, the output is going to reflect or follow the data. So if we have a 0 in, we're going to get a 0 out. If we have a 1 in, we're going to get a 1 out. So once enable is activated, the output follows the input. Think of it like a window. That's why it's called a transparent latch. When the blinds are open, you can see what's on the other side. Here, if D is 1, the output's going to be 1. If D is 0, the output's going to be 0. Let's take a look at the waveforms down here and see if we can fill it in for a D latch. Once again, we're going to start Q off low. So it's going to stay low until something happens. First of all, we need enable to be active in order for any of the outputs to change. So during these 6 time periods here, our output is going to follow our input. Again here, and this last time period at the end. So at this first change in the enable pulse, we're going to follow the output. Q is going to follow D. So D goes up high, drops down again. For 3 periods it stays low, then it goes up. Now what happens is enable has dropped off. So it doesn't matter what the data does while enable is low. It's going to hold whatever value it has until enable is active again. So we're going to hold that high until we have another change in enable, which happens right here. So at this point, it's like having our window again. We're going to let this input become visible on the output. So the output's going to go low. Now, enable becomes inactive again for these 3 periods, which means we're going to hold whatever we had before. So we're going to hold that low. Enable goes high. We're going to let the input show through. So we're going to stay low because our input is low for those 2 time periods. Enable becomes inactive, so we're going to hold the value we currently have, which is a 0. And then finally, enable goes high again, so we're going to let the input show through. It's still low. So we have 2 points where we actually saw that data show through. Let's take a look at what's inside a D latch. The first thing you should notice is that we have a NAND latch here with its active low set and its active low reset, giving us either a 1 on Q or a 0 on Q. Now if we look at what's feeding those inputs, we see 2 NAND gates. So we know that we have an active low output here, and that's going to generate a low when D is high at the same time that enable is high. If we look at the second NAND gate, we're going to get the active low we need on reset if enable is high at the same time that D is low. So we can see by adding this inverter in here that we've ensured that we never get a set at the same time that we get a reset. So by doing this, we've prevented that instability that we had with a set-reset latch all by itself. So what happens if enable is low? We know from before that the latch should just hold on to what it has before, but how does it affect this front-end circuitry? So if this is low, it means we're never going to get a set here, or we're never going to get a reset here. So when we have an inactive input on set, an inactive input on reset, we know that our NAND latch is going to hold whatever it had before. So our D latch very nicely looks after all the cases we had with our NAND latch, plus it eliminates the instability. So we've been talking about the latch as a storage device, and so let's put some latches together to form a more useful device. So what we can see here is we have 4 independent D latches. Each of them are connected together with a common enable, which means we're going to turn them on and off all at the same time. We have 4 independent data bits coming in, labeled D3, D2, D1, and D0, and those are representing a 4-bit binary value that we know, because there are 4 bits, can be anywhere from 0 to 1111, which is F hexadecimal or 15 decimal. So we have a very small system here that we can use to store a hexadecimal digit. What isn't shown on here, though, are our outputs. So we have Q3 would come off here, Q2 would come off here, Q1 here, and finally Q0. So what happens with our system, if enable goes high, each of the 4 latches are turned on. They sample what's coming in on the data lines, so we would sample D3, D2, D1, and D0, store those 4 bits, and make them available as an output on Q3, Q2, Q1, and Q0. So if we come down here and look at our timing diagram, we can see our 5 inputs. Here's our enable pulse, and here are our 4 data streams. So let's take a look at the enable one first. We come across here and we have a very short pulse that is going to turn on the 4 latches for a very brief instant in time. What that's going to do is equivalent to a sample and hold. So it grabs what's on D3, D2, D1, and D0, stores them in the latch, and makes the output available on Q3 through Q0. So what it's going to do, it's going to grab what's on D3, D2, D1, and D0 at that point in time, and we're good to go. So what I'm going to do is I'm going to mark in that sample and hold point. Next one is also a sample and hold. So again, we're going to take, it's like taking a snapshot at that point in time. So let's mark that indication in. Now the next one is more like a traditional enable, where we're opening that window. Remember, this is called the transparent latch, and we're opening that window, and our outputs Q3 through Q0 are going to follow whatever D3 through D0 are doing. So from here through to here, we're going to see our outputs mirror what's on our inputs. The last 3 time periods here, enable has gone low, so nothing's going to happen. It's going to hold whatever it had before. So let's take a look at what's actually happening on each of those lines. So as normal, our outputs are going to assume to start off low. So there are our 4 outputs, Q3, 2, 1, and 0, starting low. We get to our first sample and hold point. D3 is high, D2, D1, and D0 are all low. So Q3 is going to go high, and it's going to stay high until our next enable point. The others were all low, so we'll mark those in as low. We get to our next sample and hold point. We have D3 and D2 high this time, and D1 and D0 are low, so let's mark those in. Q3 is going to stay high, Q2 is going to go high, Q1 and Q0 are going to stay low. Now we come to our window. What's going to happen? We're going to follow D3 on Q3. So let's do D3 first. So Q3 starts off high for 1 time period, low for 2, and back up to high again. We look at D2, it's high for 1 time period, low for 4. We'll fill that in, high for 1 time period, low for 4. We look at D1, very similar, high for 1, low for 4. So this one is actually going to go high for 1, back down, low for 4. And our last one is low for 1 and then high for 4. So we stay low for 1 time period and then it rises. When enable goes low, our 4 latches are going to hold whatever they had before. So we're going to hold this high, we're going to hold this low, and this high. So let's take a look at what we're seeing on the outputs. So here we can see all 4 of our outputs are low. So we're actually seeing the value 0. The next period of time we have high, low, low, low. So we have 1, 0, 0, 0, which means we're seeing an 8 on our data values. Next period of time we have high, high, low, low. So we have high, high, low, low, which means we're storing a C or a 12. Next set, we have changes. So we have high, 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 low. And we seem to have lost our trace here, so let's put that back in. So here we have high, 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 low. So we have an E at that point. Then we have low, 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 high. So then we have a 1. Then we have 1, low, low, 1. So we have a 9. And finally, we have a 1, 0, 0, 1. So it holds that 9. So we can see that our value has stored a 0, then an 8, then a C, then an E, then a 1, then a 9, and held that 9 through. So this shows us very simply that a D-latch, we can take spontaneous samples or instantaneous samples, or we can enable them to watch a data stream flow through the device. So as we move forward, we'll see that combinations of latches together are providing us with some fairly useful devices.